This problem is going to be a good review of the Lagrange error term, just to refresh your memory. When you're finding your Maclaurin series and your Taylor series, you can find an upper bound on your error by using this formula from your formula sheet. It's under your options section. Okay, so if we go back to this problem and take a look at what it wants me to do. So it says the function is defined by, and it gives me a nice function, and it says write down the magic words of IB testing, write down the value of the constant term in the Maclaurin series for f of x. Well, you kind of have to remember what the Maclaurin series is. Okay, so this is a Maclaurin series. This first term would be your constant term. Okay, this one clearly has an x squared, and so on. Okay, so what we need to know, all they're asking is f of 0. So they obviously seem to think that I can just write that down and they'll believe me, that I can figure that out. So you can just substitute in 0 to find it. I do want to point out that you can simplify this particular function to make it easier, because you know you're going to be taking a lot of derivatives. Okay, and so if we use our rules for logarithms, it can greatly simplify our work when we're taking derivatives. So I could change this to the natural log of 1 minus the natural log of 1 minus x. And so when I do that, the natural log of 1 is 0. So the function itself can just be simplified to be negative the natural log of 1 minus x. Now that doesn't particularly matter as far as doing the very first part of the problem. I could do that just as easily with or without the simplification. But when I go to take a series of derivatives, it's going to be a lot easier to take the derivative of this than it is to take the derivative of this, just algebraically simpler. Okay, so back to the first thing that it asked me to do, it said write down the constant term for Maclaurin, and Maclaurin implies that you're centering it around 0. So either way you want to do it, you can substitute in the 0 here before you simplify it, or here, since I bothered to simplify. I'll just say it's the negative of the natural log of 1 minus 0, just substituting in 0 right there. So it's just the negative of the natural log of 1. Natural log of 1 is 0, so good old negative 0, affectionately known as 0. Now, I wasn't required to show any work for that. You could have just said, probably maybe easier here, substitute in 0, so you have the natural log of 1 over 1, natural log of 1 is 0. So you could have just said f of 0 equals 0. So that's the first part. The second part says, find the first 3 derivatives of the function and hence show that the Maclaurin series for f of x is this. Okay, so they're telling you the answer. So just start taking derivatives, and that's where, like I said, the fact that I've already done this is going to help me out. Okay, because when you take the derivative, okay, so just I'm going to turn to the formula sheet and remind you, when you take the natural log of x and then you take its derivative, it's just 1 over whatever you're taking the natural log of, and then chain rule would say times the derivative of what you're taking the log of. Okay, and so when I have this, I already have this negative 1 in front, and then when I take the derivative of ln of 1 minus x, then I would have 1 over 1 minus x, and then times the derivative of the inside function, so times the derivative of 1 minus x, which is just negative 1. And so negative times negative cancels, and I just have 1 over 1 minus x. Okay. Now I've been told to take 3 derivatives, so it's going to be a lot easier to take the derivative here if I just make that 1 minus x to the negative 1. And then I'm ready for the second derivative. So we'll just use the power rule. We'll bring the negative 1 to the front. 1 minus x, the power goes down by 1, times the derivative of the inside. Negatives cancel, so you have 1 minus x to the negative 2. And I'm also going to write that as 1 over 1 minus x squared. Now this is the more convenient form for taking derivatives. This is the more convenient form when I have to evaluate these derivatives at 0. And so one more time. Have triple prime of x. So I bring the negative 2 to the front, 1 minus x to the negative 3, times the derivative of the inside, so you have 2 times 1 minus x to the negative 3, or 2 over 1 minus x to the third. Okay. Now we took the derivatives like they asked us to do now. We need it for the Maclaurin series. So if you remember on the Maclaurin series, it just means that you've centered around 0. And so you're going to substitute in 0 to all of these derivatives. So we already have that f of 0 was 0. So f prime of 0, just substituting 0 right here. So 1 over 1 minus 0, 1. And then this guy right here, we would have 1 over 1 minus 0 squared, so 1. And our last little guy here, 2 over 1 minus 0 cubed, so 2. So we have all of those, and then you can just get the formula for Maclaurin series. Right here, I like to just copy it down because sometimes people will forget that you have to divide the coefficients by the factorials. So I'm just going to write it down just like it says on the formula sheet. So I have f of 0 plus x times f prime of 0 plus x squared over 2 factorial f double prime of 0. And then that's all it gives me on the formula sheet, but I can continue that pattern. X cubed over 3 factorial f triple prime of 0. Okay, and that would give us really an approximation. Okay, and so just substituting into there, f of 0 was 0, and so here I would have f prime of 0, which was 1, so 1x, and then f double prime of 0 was also 1, 2 factorial is just 2, so 1 half x squared, f triple prime of 0 was 2, so there we have x cubed, we've got 3 times 2 times 1 is 3 factorial, and then we have our triple prime of 0 is 2, so the 2's cancel. So altogether I have x plus 1 half x squared plus 1/3 x cubed, and that is exactly what they want me to show. So we have completed B. Okay? So that's an approximation for this function that we started with using a power series, a series that is built on polynomials. Okay, and so here it says use this series to approximate the value for ln of 2. Okay, so I want to find ln of 2, so basically I want to know what would I have to substitute in for x right here so that this would be 2. So I would know whatever this x is, that's what I would substitute in here to get a nice approximation. Okay, and so if our function is ln of 1 over 1 minus x, okay, I want to figure out what that would have to be for me to figure out ln of 2. What would x have to be? So 1 over 1 minus x would have to equal 2. Multiply both sides by 1 minus x, so you'd have 1 equals 2 minus 2x, just distributing the 2. And then we could subtract 2, so we'd have negative 1 equals negative 2x. Divide by negative 2, and you would have x equals 1 half. So basically, all we have to do to have an approximation for natural log of 2 is put 1 half into this polynomial. Okay, and so we would have f of 1 half would be a half plus a half times a half squared plus a third times a half cubed. Okay. And so when we do that, we can of course just do it by hand, but this is paper 3. You do have a calculator. I'm just going to let you take your time with that, either by hand or put in your calculator, but that is 2/3. So basically our approximation for the natural log of 2 using this power series is 2/3. So finally we get to what I said we'd be reviewing here on this problem, which is use the Lagrange form of the remainder to find an upper bound for the error in this approximation. Okay, so what we're going to do here is we're just going to write that down from the formula sheet. So I'm going to write this guy right here down. So to get the error, this will be, if you use 3 derivatives, this will be a 3 right here. So this will give you the error in a power series where you have gone to the n being 3, power of 3 being your highest power. Okay, so this is the n plus first derivative evaluated at c over n plus 1 factorial times x minus a to the n plus 1, and they're pretty good to us here. They tell us where c lies between a and x. We need to think about what each one of these variables is. Okay, so a is whatever you are centering the power series around. Okay, so for us, if that's Maclaurin, that's 0. Okay, the x is where the function is being evaluated. For us, we substituted in 1/2, and so our x is 1/2. Now, when it says c lies between a and x, it's whatever makes this overall function as large as possible. And generally speaking, it's either going to be a or x. You're just going to decide which one of those values would make this the highest. Now, n is the degree of the power series that you use to evaluate. So since we found 3 derivatives, and if you look, you can see this was to the power of 3, then our n is 3. Okay, it's just the highest power of your approximation that you did for your power series. And so we have all of that. I can definitely see here, let's just plug in what we know. I'm going to need the 4th derivative evaluated at c over 4 factorial. Here, this is going to be 1/2 minus 0 to the n plus 1 again, so 4. Okay, so I'm going to need that 4th derivative. So I'm going to go back over here. I had the 3rd derivative was 2 times 1 minus x to the negative 3. So I'll go ahead and take the 4th derivative. So that would be negative 6, multiply here, 1 minus x to the negative 4 times the derivative of the inside. Okay, so this would multiply, give you a positive 6 over 1 minus x to the 4th. Okay, so that's my 4th derivative. I'm just going to rewrite that, putting in a c, and then I'll decide what would make it largest, anywhere between 0 and 1/2. So if we substitute that in, we'd have 6 over 1 minus c to the 4th, 4 factorial, 1/2 to the 4th. Okay, so if we think about this, we're either going to put in, c is supposed to be something between 0 and 1/2. If I put in 0, then I would be dividing by 1, so that wouldn't change it at all. If I put in 1/2, I would have 1 minus 1/2, which is 1/2. I'm going to raise that to the 4th. Okay, so 2 times 2 is 4, times 2 is 8, times 2 is 16. So I would be dividing by 1/16, which is the same as multiplying by 16. So that's definitely going to make my error term larger. So in this case, the correct thing to do would be to substitute in the 1/2. So if we do that, we have 6 over 1 minus 1/2 to the 4th times 4 factorial over, multiplied by 1/2 to the 4th. Okay. If you work that out, again, you have your calculator, you get 0.25. So what we have here is an upper bound on the error. Okay. And the last thing it said is, how good is this upper bound as an estimate for the actual error? Well, to figure out, let's just find the true error of this problem. So the error is just the ln of 2 minus the approximation that we found, which was 2/3. Now you're just going to type this in on your calculator. Okay, just type in natural log of 2 minus 2/3. You get that we're actually not very far off at all. Okay, so this as our error, we are way, way, way under that. Okay, so the upper bound for the error is much larger than the actual error, and therefore not a good estimate.